Hi everyone, welcome to the third of 4 videos looking at some past exam questions on orders of reaction and rate equations. As you can see in this question we've got a graph, so this is a little bit different. Again, they've given us a rate equation here, and we've got some data. They've done some experiments, they've changed the concentrations, and they've measured the rate, and they've plotted it on a graph. So this is just a different way of providing us with the information. It's very similar to what we had in the previous videos, but instead of information being in a table, it's here in the form of a graph instead. What we actually need to do for this question, again, is to calculate the rate constant. Okay, so it's actually the same question that we've seen before, we're just using information in a different format. Okay. So as we've seen in the previous videos, if you want to calculate the rate constant, what we need to do is rearrange the rate equation. Okay. So our rate equation from up here, we said is always going to work out the same. K is going to be the rate divided by the concentrations. Okay. So we're going to have our rate constant K is going to be equal to the rate divided by H2 to the power of 1 and NO to the power of 2. What we then need to do is then substitute in some values to be able to calculate this. And instead of getting these values out of a table, we're going to have to get these values from the graph. Okay. And similarly to how we discussed on the previous video, it didn't matter which row of the table we chose, we should still end up calculating the same value for K. Here, we can choose any of these points on the graph, and it shouldn't matter, we should still end up with the same value of K. What I would suggest though is if we have a look at this graph, we can make our life a bit easier depending on which point we choose. If we pick a point where it's immediately obvious what the values are, and we don't have to look at it and think, hang on, is that 1.2 or is that 1.4? I'm going to choose this point here because it's very clearly 6 times 10 to the minus 4 on this axis, and it's also 6 on this axis. So that's nice and easy. So to fill this in, then we need to know what the rate is. Here the rate is on the y-axis, so the rate is going to be 6 times 10 to the minus 4. Be very careful, don't miss that off. That's a common mistake. So it's 6 times 10 to the minus 4 for the rate. The concentration of H2 is what they've told us here, so we can put that straight in, 2 times 10 to the minus 2. And the concentration of NO is also 6, but again, that's also times 10 to the minus 4. So do be careful, watch out for that. And also remember from our equation here, the concentration of NO needs to be squared. Right, and so we just need to calculate that. I'm going to work out the bottom of this fraction first. 2 times 10 to the minus 2 times 6 times 10 to the minus 4 squared. And then we're going to do 6 times 10 to the minus 4 divided by that. And we end up with a value of 83,333. And our question here, it says, give our answer to 2 significant figures and in standard form. So do be careful with that. They do try to put it in bold. They're not trying to catch you out, but you do need to make sure you've actually read that, because a lot of people just go straight ahead and write that down as their answer. And that's a bit of a sad reason to lose a mark, just for not reading the question. So 2 significant figures, so it's going to be 8.3 times 10 to the power of 1, 2, 3, 4. Okay. Then we also need to work out the units. As we've seen in the previous video, to work out the units, we substitute the units into the expression instead of substituting in the values. Okay. As always, units of rate are moles per decimeter cubed per second, and the units of concentration, moles per decimeter cubed, and moles per decimeter cubed again, but that one needs to be squared. Hopefully you're getting familiar with this kind of method by now. What we're going to do is we're going to cancel out one set of moles per decimeter cubed. So we're going to have seconds to minus 1 over moles per decimeter cubed squared. Then, because it's on the bottom of a fraction, we can say that's equivalent to being to a negative power, so it'll be to the power of minus 2. And then we need to sort out this bracket, and we're going to say seconds to minus 1, moles to the minus 2, decimeters. Remember, we multiply powers when we're in this situation. So minus 3 multiplied by minus 2 is positive 6. Then, as we said, the standard way of writing this is to write it with the positive one first.